So we were discussing some redundant fields that are no longer in the IPv6 packet header, the fragment offset, are redundant and removed. Why? We don't have fragmentation with IPv6. The header checksum removed, redundant, because we have error check, error connection. At layer 2, we have that. At layer 4, we also have that. Why do we need it at layer 3? So IPv6 does not have that. And all this leads to a simplified header, which means, what was the statement here? Simplified header, which means improved packet handling. If we have less fields, it means improved packet handling. Right, let's go to the fields themselves. We have the version which we had with IPv4. In this case, it's version 6 and the number 6 in binary there. The traffic class with IPv4, we had TOS, diversity. I know TOS, it was diversity what? Differentiated services, not diversity. DivServ, differentiated service. It's just a different name with IPv6. With IPv6, it's traffic class, classification of traffic. The same use, quality of service. We have the flow label. This is a new edition. It's not there in IPv4. Typical question, which fields are in IPv6, which are not in IPv4? Which fields are in IPv4, which are not in IPv6? Comparison. Those type of questions, they do come. So answers, flow label. It's there in IPv6, but not there in version 4. It informs the device to handle identical flow labels the same way. It's a 20-bit field. So basically, traffic from the same IP address and destination MAC, we call that a flow. So if traffic is coming from the same source and destination, it's called a flow. It is given a label so that we can easily process that information. So traffic from the same destination and same source, they are given a label. It results in easier handling of identical flows. Identical flows, they can be handled much easier. Different flows, different characteristics of traffic, different ways of them being handled. But if the flows are the same, without the labels, you won't know if the flows are the same. So it's difficult handling because you don't know. But with the labels, you know the way you are treating traffic A is the same you treat another type of traffic, which is labeled A as well. Basically, that is what it translates to. Now, payload length. This is very important. This is a very important concept. But the security, okay, we won't do security. In security, in network security, flow labels, they are very important. Right, payload length, that's the payload length. 16-bit field indicates the length of the data portion or the payload only. The next header, the next level protocol, we have that in IPv4, the hop limit, same as the TTL. So in IPv4, we have the TTL. In IPv6, we have the hop limit. TTL, time to leave. Source and destination IPv6 addresses, we know those. Let's go. IPv6 packet may also contain extension headers. Extension header characteristics include they are optional and provide optional network layer information. They are placed between the header and the payload, may be used for fragmentation, security, mobility, support, etc. Unlike IPv4 routers do not fragment IPv6 packets. All right. Why we have these extension headers? extension. If, for example, you want more security for your packet, you have an option to add an extension. It might not be necessary. Therefore, it's an option. With IPv4, we don't have those extension headers. Everything is necessary, meaning even if it's there and it's not being used, it just leads to overhead, and that's a problem. Here, it's an option. If you don't want it there, you can remove it. If you don't want anything to do with security for your packet, you just remove the header, less overhead, easy handling. If you don't want your packet to be fragmented, easy handling. Why are these two things conflicting? Maybe used for fragmentation, routers do not fragment IPv6 packets. At times, an IPv4 packet can be sent over an IPv6 packet. Therefore, this packet will need some fragmentation because we can fragment this. Tunneling, what is it called? I think it's called tunneling. When we send a version 4 packet over a version 6 packet, it's supposed to be called the tunneling research. All right, so extension headers basically it's an option given to IPv6 packets where you can add some information. It's an option. With IPv4, we don't have those options. It's either it's there or it's not. So with IPv6, we have that flexibility because we can add it or we can remove it. All right, how a host routes, packets are always created at the source. We know that each host device creates their own routing table. A host can send packets to the following: itself, localhost, remote host. So a device can send a package to itself. We call that a loopback. Testing to see if everything is proper on the link that the host is connected. It's a loopback interface. It's a loopback IP address. If you see an address like this, 127.0.0.1, that's the loopback IP address. A packet can also be sent to a local host. When we talk local, that's a local network. So here, a local host is sending from here to here. The destination is on the same LAN. We can use MAC addresses. Lastly, remote. We are sending to another network. We have a router there. It means we have different networks, this one and this one. If you are sending remotely, then you need a layer 3 device. So a host can send packets via the following: to itself, loop back, to a local host, then to a remote network. The source device determines whether the destination is local or remote. Method of determination: source uses its IP address and subnet along with the destination and IP address. With IPv6, source uses the network address and prefix. Local traffic is dumped out the local interface. Remote traffic is forwarded or directed to the default gateway on the LAN. So what are we saying? The source determines whether the destination is local or remote. If you are given an IP address, so let's give the network here, let's call it 192.168.10.0.24. That's the network ID. And the host is 192.168.10.10. This host belongs to this network. How do we see it? They have the same prefix. How do we know? We use the subnet mask. I think that's a discussion for later. We know. So if we have the same subnet mask, if we have the same prefix, the same network ID, it means we are in the same network. If we don't have the same ID, it means we are in two different networks. That is now remote communication. So for example, if I come to this end, okay, this network is 10, so let's make this one 20, logic. Let's make this one 20, because they are different networks. So with this one, The network is 10.0. This one is 10.10. This one is 10.15. You can see 10.10, 10.15. These numbers, they're the same. It means we're in the same network. So how does the source determine if the destination is local or remote? If the source and destination, they have the same network ID, it means they are local. So these two are local. But if they have different, let's put the IP address from this one right here. It's 192.168.20.10. If you compare this, they are different. That basically means a remote network. Now, if we're in a local network, traffic is sent direct to the other local host. So if we are local, for example, right here we are local. If I want to send to this device, we are local. So I send directly to that. Even my packet, here's the destination of this, the source of this, right? No problem. If I'm sending to this remote, traffic is first directed to this interface, and the router does its primary role of routing. It then forwards to this network. I think we've touched on how it forwards. It looks at the routing table. Where is the network in the routing table? It forwards to that specific interface. Right, a default gateway, that's the gate out of the network. It has the following features. It must have an IP address in the same range as the rest of the LAN. So if this is my LAN, okay, let's use an example which is there already. This is our LAN. This is the default gateway, dot one. Dot one meaning 192.168.10.1. The IP address of the default gateway should have the same network ID as the devices in that LAN. So this 192.168.10 is the same as this here, is the same as this here. If it's different, then it means that's a wrong default gateway. These devices here will not be able to go out of the network because there is a wrong default gateway there. Characteristic number 2, it can accept data from the LAN and it is capable of forwarding traffic off the LAN. It receives traffic from the LAN, you forward it to other local area networks. It can route to other networks, we know. If a device has no default gateway or a bad default gateway, its traffic will not be able to leave the LAN. Kana personal default gateway, you can communicate locally, but you cannot communicate remotely. So the default gateway, very important. A host will know the default gateway either statically or through DHCP. Statically, I think particular configurations, a basic configuration, even particular configured SVI, we statically manually configure the default gateway on our switch and as well as on our PCs. Our PCs kind of IP configuration to this IP address. That was manually configuring IPv4 address. We can as well use DHCP, where the dynamic protocol is used to dynamically assign IPv4 addresses. With IPv4, we have DHCP. With IPv6, we have router solicitation. It's sort of the DHCP of IPv6, automatic address assignments. Right, the default gateway is static route, which will be a last resort route in the routing table. When we talk of a last resort route, let's say you have a packet in this network. You want to send, let's say we have two devices, .10 and .15. Then you send your traffic from PC1 to an address 192 168.10 no, let's put .20 .11 and address destination. This is the destination. What does the PC do? It sends to the default gateway. Why? That is a last resort route. If an IP address is not in the local, therefore it is forwarded to the default gateway because that is the last resort route. Kana packet rashayabwe kuenda within the local area network, runoenda last route, which is the default gateway. So packet rese rikatendera rikashaika riri kuenda ipi locally, rinogumira panapa. I think it's sort of the same statement as the Rushanda, but the get out of the network, the last resort route. Okay, all devices on the LAN will need the DGW of the router if they intend to send traffic remotely. Okay, right, host routing tables. On Windows, we can use the netstat-r. We can as well use router print. 3 sections displayed by this. Right, to display routing table of a host, you can do this. Let's have command route print. We just display that same thing. It gives us, if we have the network destination and the interface which is being used. If I want to go to this IP address 000, which is the default gateway, which is the default route, then I'll use this interface. If I want to go to, this is the Lübeck network, Lübeck IP address, okay, use that same IP address. If I want to go to this 127, that's another Lübeck, that's the range of Lübeck. If I want to go to 192.168.0.0, I'm not sure what is the IP address of this. I will use this interface. And I think this interface 192.168.0.140 should be the IP address of my PC. Let me see. We only have power. IP config. IP config. What am I doing? IP config. All right, 192.168, that's my IP address there. All right. Then my default gateway is 192.168.0.1. So interpreting information in app is just showing you the routing table. It shows you the map of the network. Kuti kana unoda kuenda kwakati unoenda sei. So if I want to go to this network, I go through this interface in Rapper. It can easily be best explained using my routing tables, EMA routers, not EMA hosts. I think we'll get there and we'll get to explain that. Right. Okay, so we were talking about how to show your routing tables, host routing table. This is how you show them. I don't think this is very much important at this point, but the routing table which is used by a router, not a host, that will be very important. So, panapa tine host app, that's a PC. A routing table of this is not as important as routing table of this. Two different routing tables. This one is very important. Do you to focus on? Right. Introduction to routing. What is routing? Choosing the best path to a destination network. What happens when the router receives the frame from the host device? So I'm just going to summarize what happens. Packet arrives on the Gig Ethernet interface of router 1. It de-encapsulates the layer 2. Router 1 examines, router 1 encapsulates. Okay, we've been going through this whole time. Routing, this PC encapsulates information. Our message, we have our message, HTTP. We want to, no. Let's say we want to send a video to this PC. What happens to this video? This video from the application layer, it gets encapsulated, goes through all the layers up until it gets to layer number 3. Since we are focusing, no, with the PC, it gets to layer number 1. Layer number 1, physical layer, it gets transmitted. It gets to this switch. We won't focus on layer 2 because this is the layer 2 device. We want to focus on layer 3. From layer 2 device, it gets re-encapsulated, goes to the router, right? Let me go back. From this PC, we go to from the application to the physical. Physical, it goes to layer 2 switch. From layer 2 switch, we de-encapsulate from the physical to the data link. Then it goes back to the physical, re-encapsulation. Then it gets transmitted. Here, it gets de-encapsulated. When de-encapsulation occurs, we will be looking at the IP address. What is the destination network ID? We use the destination network ID to forward to the next network, right? So the destination network ID, in this case, if we are sending to PC2, it will be 10120. That is the destination network ID. However, kana tiri router panapa, we don't have this destination network ID. What we have kana tiri router panapa, we have this network that we know, which belongs to this interface as well as this interface. On this side, we have this network that we know, which belongs to this interface. But hatizivi. How do we get there? How we get there, we have my configurations a routing atonoita. So routing, what we can do, we can compare this device to configure a routing, a static route. Let's start with a static route, which we can configure manually. So basically what we'll do, we'll say if R1, you want to go to 10, 1, 2, 0, 24, which is this network. You go via 209.165, 200, 224, which is this network. So since we are trying to go here, when I get to this device, I know that I have to go through this to get there. So by going through this, it allows me to get here. And when I get here, I can easily see this network. So when we talk of routing protocols, configuring static routes, basically what we are doing is telling networks beyond what you can see. How do you get to other networks that you cannot see? That is routing. Let me give another example. I think things start to get a bit complicated with routing, a bit complex. So if I have a network like this, network 1 and network 2, I'm trying to send information from network 1 to network 2. This router here, it knows network 1 and network 2. How does it know it? Because these interfaces are directly connected to router 1. So information ikabva panapa ichida kuenda uku, ichikasvika parouter apa, router rinotoziva kuti iri kuenda uku because router is directly connected to that interface. No need for routing in routing protocols there. For a change, now if we might need this. right? For a change, if we have something like this, network yedu yakura, network 1, network 2. Kana network yedu yakura, this router iri rinoziva this network and this network only. Iyi network ishi haizikanwi ishi. Iyi network ishi inozikanwa ne-this router. Isusu we are trying to send information from this network right here to this network. But information yedu kana pasina kuconfigure routing or okay, general, kana pasina configure routing, traffic painosvika panapa, it gets stuck. Why? Because router it does not know where to forward that traffic. Haizivi, it only knows these two. And if this network is say 3, router ready inoziva network 1 and 3 only. It does not know network 2. And the router does not forward to a network it does not know. Router kana risingazive network hariforward ikoko. So how does the router know? It knows by my configurations that know my routing protocols. So basically what we will do in this case, to nepa router app, to configure kuti if you want to go to network 2, you go via network 3. So information painobva panapa ichisvika app iri kuenda ku2, but painosvika panapa inoziva kuti ndisvike ku2 ndichapfuura nepa3. Once ndangosvika panapa ndatosvika pa2 because this router rinoziva kuti pane network number 2 iripo. I think that's a summary of what routing is. Patichazoproceed tichienda to the higher levels, we will now put my network addresses instead of these numbers. These numbers, they were just for simplification. So here there'll be a network 192.168.20.0. Here there'll be a network .10 24. Here there'll be another network .30 24. So if I want to get to .10, I go via .20 basically. That's how you configure my routing protocols. This is static. If I want to go dynamic, a dynamic routing protocol, it automatically learns kuti kune network iriko. How does it automatically learn? Messages are sent. So my routers, they exchange messages. Routers exchange messages. So router iri rinosendera a message uku kuti inini I know network 2, I know also network 3. Panapa tandamboisa network 3. Iri rinosendera iri. Then iri wo rinosendera iri. Kuti inini I know network 1 and I know network 3. So muma routing tables, the information that will be there. Routing table yepanapa ishi inenge ine network 1 tinoiziva, network 3 tinoiziva. Tinoziva zvo network 2 tinoiziva sei? Tinoiziva because hama yedu iyi yataura kuti tinoiziva. Saka isusu kana takuda kusenda ku2 tinocontact hama yedu inotisvitsa. So zvireva kuti tinoiziva by connection. So we also know 2. Kunokuwo iyi inoziva network 2, inoziva network 3 by direct connection, ukama hwepedyo. But tinoziva izvo 1 neukama hwemaconnection. So at the end of the day, my network ese anenge ari kuzivikanwa dynamically. So every router rinenge riri kuexchange information with another router. This is what dynamic routing protocols basically are all about. Tichasvika where we will now put numbers, where we will now put more configurations. It's just important at this point to understand how information is being routed. I hope that summarizes Njiri for step 1, 2, 3. Right, 3 types of routes. Tatumabata 3 types of routes. We have 3 types of routes. 1, directly connected. Where's my case? Okay. We have what we call a directly connected route. Directly connected route, a route automatically added by the router provided by the interface. My routes are. One is my directly connected. Are direct connected router yako ma-interface wayo ndoanonzi ma-directly connected routes. Then ma-remote, in this example, if I'm looking at this router, this is a remote route. These are routes the router does not have a direct connection and may have to be learned. They can be learned manually or dynamically. We've gone through that. So a remote route, route is still directly connected. So for example, if I'm looking at R1, then this is a remote route. If I'm looking at R2, these two are direct. This one is remote. Then we have a default route which forwards traffic to a specific direction when there is no match in the routing table. So the default route, kana tashaya match in the routing table, kana, let's say I want to send information to route number 1, but routing table inoziva 3, 4, 5, ndo anoziva. It means there is no match in routing table. We don't know number 1. Therefore, this is sent to the default route. And the default route ndo rinenge rine IP address yakanzi 0000. I think you've seen this. Mashuro. Keep this in your head. Default route, very easy. 000. That is what we call a default route. I think pataisa netstart here. Route print, ndo pataona this IP address. It's a default route. Right? Static routes characteristics, they must be configured manually. So we have static, we have dynamic. Static, manual, must be adjusted manually. Good for small networks, often in conjunction with a dynamic protocol. So this is the command rinoshandiswa pamastatic routes. IP route, this is in example yanga ndiri kuexplaina. We had 2 routers. And I said, this is 3, this is 1, this is 2. We want to go from 1 to 2. But as it stands, this router is 2. So we have to configure a static route. This is an example of a static route. So this static route is saying, IP route, if you want to get to network number 2, you go via network number 3. That is what the route is saying, basically. So that's a basic command, static route. Very important to know now. Static routes are good for small networks. So kana ndine ka small network ndokwanisa kuya parouter panapa kuti kana uchida kuenda kunetwork number 1 unopfura via network number 2, uchida kuenda kunetwork number 5 unopfura via network number 4, etc, etc. But kana una 1,000 routers, you cannot make 1,000 configurations on every router times 1,000 routers. That's how many million configurations that you can make on every router. Kuti kana uchida kuenda kuna ningi unopfura nepana ningi, unopfura nepana ningi uchiita sei. That's why we have my dynamic. My dynamic, they are easy. Why? Because there is exchange of information between my routers. Exchange of messages. Those are what we call routing protocols. We'll discuss mainly CCNA, discuss mainly OSPF as a dynamic routing protocol. So ndo rachite. This can also a very huge network. Shanda OSPF. Because my routers are not going to you don't have to manually configure routes one by one. Let's finish up. Dynamic routing automatically dynamic routes automatically. They discover remote networks, maintain up-to-date information, choose the best path, find new best paths when there is a topology change. This one, yakanakira nyaya topology changing. If we add a router panapa, doing this topology change, if we add another router panapa, kana pasina static route, kana pasina static routing yekuti we've added another router, kana uchida kusvika ku 1 and 2, unoenda via R1, which interface A, B, C, D. Kana pasina izvozvo, you will never be able to communicate with these two. But kana pane dynamic routing protocol, router iri richingoiswa munetwork chete, rinototanga kucommunicata neiyo. Kuti inini ndinoziva 1 na 2 kuno. Zviro kuti uyu akutozivawo. Uyu oudza uyu kuti inini ndinoziva 1 na 2 because uyu anoziva 1 na 2. So tese takutomuziva. Saka iyi kana chida kusendera kuna 1 na 2, it goes here first, then inini ndoziva uyu ndiyakandiudza, then we get to the final network. I'm really trying to simplify this. Kana takuzopinda deep, We'll probably not have time to simplify as much as I'm doing now. Introduction to IPv4 routing. Right, so my tables, they have my symbols and a shandy square. I hope this is the last one. Thank you. They have my symbols and a shandy square. If an interface is directly connected, you know, shandy square L. So this is a directly connected interface. Then L 255.1. 255.1 the ish, then 255 E rapper. Then directly connected networks. This one is for directly connected interface, L. Connected networks, then we are looking at this. If you go and check, no, my numbers are up. Directly connected. Then Kanaina O, it means it's a dynamically linked route using OSPF. Kanaina S like this, that's a gateway of last resort. And I think we have less than 1 minute. Let me just conclude there. And this is layer number 3, network layer.